Hey there, physics people. Mr. Simon checking in. We're talking about, at this point in our class, the law of conservation of energy, potential energy, and kinetic energy. And as we know from our class discussion, potential energy is mass times acceleration due to gravity times the height, mgh. And kinetic energy is 1/2 the mass times the velocity squared, 1/2 mv squared. We know from the law of conservation of energy that energy can't be created or destroyed, it just gets transferred from one form to another, and the total energy in a system remains constant. A great way to illustrate this is with something we call a pendulum. A pendulum, as you probably know, is simply a mass on the end of a string, or in this case, a bowling ball on the end of a 16-foot long cable. Pendulums do a great job of showing us both potential and kinetic energy and the transfer from one form to the other. So you take a look at a pendulum. At the very top of its path, we know it has to come to a stop. If it doesn't come to a stop, it can never change directions. So we know at the very top of its path, when it comes to a stop, the velocity is zero. Well, if the velocity is zero, the kinetic energy, which is a product of the mass and the velocity squared times 1/2, has to be zero as well. So it has absolutely no kinetic energy at the very top of its path. All of the energy is in the form of potential energy, which as we know is mgh, and it certainly does have its maximum height. So at the top, maximum potential, minimum kinetic. As it goes down in its path, it's losing height, therefore losing potential energy. But it's picking up velocity, therefore gaining kinetic energy. So it's transferring from potential energy into kinetic energy as it goes down. At the very top of its path, at the very bottom of its path, for all intents and purposes, its height is zero. Close enough we can just call it zero, which means the potential energy at the bottom is zero. We also know it's at its maximum speed. So now it's lost all this potential energy, converted it all into kinetic energy. Then the way up, it's going to do just the opposite. It's going to lose speed, therefore lose kinetic energy, but gain height, therefore gain potential energy. So it's a constant transfer from all potential at the top, losing potential, gaining kinetic, all kinetic at the bottom, etc. As this pendulum continues to go, as you know probably just from your own experience and from logic, the pendulum is eventually going to come to a stop. Now this one's going to go for quite a while, but if we let it go for another 5 or 10 minutes, the motion is going to look more like this, and after 5 or 10 more minutes it's going to come to a stop. Well, if it's at a stop at the bottom, it's got no kinetic energy because it's not moving, and it's got no potential energy because it has no height. Does that mean that we've lost energy? Well, we know from the law of conservation of energy, we can't just destroy energy. It's got to go somewhere. What happened in this case? Where did the energy go, or what caused the motion of the pendulum to change from a lot greater height and speed to what it has right now? So pause the video and give that some thought. What made the pendulum appear to change? Now, what you probably have thought about, as students have thought in the past, are two things. Students will guess often that gravity has played a role in this. Gravity has brought this thing to a stop or slowed it down. But that's not right. So gravity does, in fact, slow the pendulum down on the way up, but it also speeds it up on the way down. And it speeds it up at the exact same rate on the way down that it slowed it up on the way up. So gravity actually does not play really a role in slowing down the motion of the pendulum. Another thing you probably thought of, as students do every year, is friction, air resistance or friction as a whole. And that part is correct. So there's really friction going on in two basic ways. One point of friction is at the very top, which you cannot see, at the pivot of the cable, there's some internal friction. That doesn't account for a whole lot of friction, but that is some friction. The main friction, as you probably guessed, is the air resistance. It's the bowling ball plowing into the air molecules, and also the cable plowing into the air molecules, just like the air resistance we talked about a couple of units ago. So the air resistance does play a role. But what does that mean? You talked about air resistance, Mr. Simon, but that's a force. What happened to the energy? Well, what happens is the bowling ball plows into billions and billions of air molecules. So the air molecules are just roaming around, having a good day as far as air molecules go. The bowling ball hits an air molecule and gives it some energy, and it speeds up that air molecules, literally just bombarding into it, which is really what thermal energy is all about. So thermal energy or heat is just an increase in the kinetic energy of molecules. So you put a pot of water on the stove. You want to bring the water to a boil and cook some pasta. The water, being a liquid, has some movement of air molecules, and as you add heat to it from the stove, you're going to increase the kinetic energy of the water molecules, and you start vibrating and moving at a much faster pace, a much greater velocity. So really the thermal energy is just an increase in the kinetic energy of the molecules. In this case, air molecules are moving around in their gaseous state, but the bowling ball runs into it just like a normal collision. It's going to give some of that velocity and energy to the air molecules. So the energy was not lost in the system when the system includes the air and the surrounding area of the pendulum. It's gone from the kinetic and potential energy of the pendulum into kinetic energy of the air molecules. So at least in theory, the temperature of this room increases every time the pendulum comes to a stop. Now, how much it increases is obviously pretty minuscule. It's not like you can heat your home by hooking up 500 pendulums and letting them go. You're not going to get anything measurable. One last thing with the pendulum, knowing the law of conservation of energy, that we cannot gain or destroy energy, that it has to stay conserved, I can do something kind of cool. I'm going to hold the pendulum right up against my head. I'm going to let the pendulum go out and come back. I know the energy of the pendulum cannot increase. So know that the bowling ball cannot gain extra height and come back and hit me in the head, as long as it don't lean forward, which I've been known to do. And I know typically it's going to give some of that energy, even on that first swing, to some of the kinetic energy of the air molecules surrounding it. So I should be able to hold this tight against my head, let it go, have it come back, and now hit my head. Let's give it a shot. Just have to make sure I don't lean forward. And then right here, right up against my forehead, I let it go, it comes back, I get nervous. Oh boy, that was really, really close. Let's try that again. I think I lean forward just a little bit. So I'm going to hold it right up against my head, let it go out, come back. Whoa. And I don't know how it looks from your point of view, but from my point of view, that's pretty scary when it comes that close to your head. So there's a little illustration about potential energy, kinetic energy, the law of conservation of energy, and a pendulum and how it all relates together.